And they're great. SciPy adds scientific functionality, all kinds of signal processing stuff, various other things, distributions. But if you compare, like, let's say 7 or 8 years ago, if you compared R to Python, the really obvious thing that was missing was like labeled arrays and good support for labeled arrays, right? In R, you've had the data frame forever, basically, where you have named rows and columns. And Python didn't have that, which made data analysis really quite difficult, or at least more difficult than it needed to be. And so Pandas is really the answer to that. And it's a really nice package that adds lots of support, lots of tools for manipulating data using complex data structures. And it gives you much better ways of working with tabular data. You can do all kinds of interesting operations. And that's what we'll cover today. So I will go through several sections in this series of notebooks. Feel free to stop at any time if you have questions. We're not bound to this. I'm happy to stop and talk more about things that are particularly interesting. And as I've said for some of the other tutorials, I'll be around the whole time. Feel free to grab me any time, even if it's small things, like you don't know why group by is behaving weird. Just come find me. I'm happy to try and figure it out. So I'll assume that everyone's installed Pandas OK. If you installed, actually if you're using the Jupyter Hub, or if you installed, I think, base Anaconda, the Conda distribution now I think comes with Pandas by default. So you should have Pandas. If not, you can always Conda install Pandas. I will assume that we don't have to worry about that here. Imports, you may have already seen this. So as you know by now, you have to import all the stuff that Python knows about that you want to use. And conventionally, Pandas is called PD, just as an abbreviation, right? So you import Pandas as PD, and thereafter, the kind of base Python, or the base Pandas object is going to be called PD whenever we access it. So we're going to do things like PD data frame, PD series, etc. Again, it's totally a convention. You could name it whatever you want. Sometimes people will just say import Pandas, but then you're just typing more characters. All right. So we run that, and now we have Pandas in our environment. And right away, you can sort of start inspecting what actually lives inside this Pandas module. And so in this case, you can see you have all kinds of stuff, right? There's tons of functionality in here. And so I will hopefully help you make a little bit more sense of this. All right. So we will start by, if we go back to this index, you'll see that there's several different subchapters that Jake's written. We'll skip some of these. Like, I think hierarchical indexing is interesting, but there's a very limited set of cases where you actually need to worry about this. And often if you do need to worry about this, you may want to rethink what you're doing and try to find an alternate way. Cases where it's absolutely necessary, but by and large, I found hierarchical indexes often can be avoided and your life is simpler. So we won't talk about that. I won't talk about missing data, which is kind of important, but gets into the weeds a bit. So much of this we'll skip, and I'll start with the basic stuff and then focus a lot on combining data sets and aggregation and grouping. But again, if there are things that you really want to hear about, then just stop me or find me afterwards and we'll talk about those. Okay, so let's start with this section 3.1 here, which is introducing Pandas objects. So Pandas objects internally store NumPy arrays, right? And so you can think of this really as like an extension to NumPy, and that's what it is. You basically get existing NumPy arrays, which hopefully all of you are familiar with. You don't have to be experts or anything. I'm not going to do anything fancy with arrays today. But NumPy arrays are sort of ways of representing n-dimensional data, and Pandas takes those arrays and just adds a bunch of stuff around them that makes it easy to manipulate that data and work with it. So usually you'll almost always import both of these things. You'll start out by importing NumPy as NP, Pandas as PD. And there are really two sort of critical objects. There are two kind of types, two structures that you'll find yourself working with over and over again. The Pandas series and the Pandas data frame. And they roughly, you can think of them as like a single column versus a table, right? That's, if you think of sort of generic language, that's what they are. A series is like one column, and a data frame is sort of multiple columns stacked together. So if you want to initialize a new series, you can do that very simply by calling series on the root Pandas module. So when you kind of construct a series, you have a variety of options for passing in data. And the simplest one is just to pass in a list of values. And I think for those of you who saw my visualization talk, I'll repeat it for those who weren't. Pandas, like most of these packages in the Python ecosystem, are fairly intelligent about treating, and there's kind of technical reasons why it's actually fairly easy to do this, but they're smart about treating any kind of list-like object, whether it's a base Python list or a NumPy array, as interpreting it correctly. So you see here that you can pass just a list, sort of a pure Python list. This is not a NumPy array, into the series, and it will know what to do with it. It'll say, oh, thank you very much. I'm going to construct a new series object from this list of values you gave me. And if we just type that, here's what we see. So these are the values we fed in, 0.25, 0.5, 0.75, et cetera. And notice that unlike the list, so if we were just to print the list itself, right, you wouldn't see this index here. That's what the list looks like. If we were to turn this into an array by passing this to the array constructor, it would tell us, hey, this is an array, essentially, right, with the same values. And when we construct a series, we get, we get those values, but we also get this additional thing here, which is called an index, and I'll talk about that in a second. But I mentioned that all the series is an array, an NumPy array, plus some stuff. And both of these objects we'll talk about, series and data frames, make that array easily accessible. So you can always get the underlying values, the underlying NumPy array values, through the values property. So in this case, we've constructed this series called data, and at any time we can ask for the values of that object, and here they are. Notice, right, this is identical. This is exactly the same thing as what we would get if we had constructed an array in the first place, and that's because it is the same thing. So when we create a Pandas series, it's internally storing that array. It's creating for us from the list, storing it as a NumPy array, and so it looks the same because it is. So you always have an array inside that Pandas data structure. And that means that sometimes you'll find yourself in a situation where you don't need all the overhead of like all the extra stuff in the Pandas object, and you have some optimized routine that just deals with NumPy values, and you don't want to. So what you can do is just grab this, pass it to your performant routine, and just work with the values and get back some result, and then create a new Pandas series. So that's quite a common pattern when there isn't where there's some chunk of Python code that only works with NumPy arrays and doesn't know what to do with Pandas data structures. Okay, I mentioned the index a moment ago. So you have this thing over here, which you don't have for arrays, NumPy arrays. You can always retrieve that thing through this index property. So if you ask for the index, here's what you get. In this case, what you get is a range index, and we'll come back to this in a second. The point is just that this is a description. This is actually the code. This is the thing that generates this 0, 1, 2, 3, right? It just starts at 0 and goes till 3. Okay. So you probably are familiar with indexing by now in NumPy. And for the most part, there are some important exceptions, but for the most part, the syntax that works for indexing in NumPy is going to work in Pandas too. So in this list here, we might want the 1th value, right, which is actually the second one, because remember, indexing in Python starts from 0. So the value at index 1 would be the second value. And so if we ask for that particular value, we get 0.5, which we can verify is in fact what's stored at this position. So just like, for that matter, just like a list in Python, but also like a NumPy array, we can index into specific positions. We can also slice, just like in Python, so we can ask for the subset of that series beginning at position 1 and ending at position 3. And what we get back is going to be a series. So when you slice, in fact, most of the time when you call some operation on Pandas series, you're going to get back another series. There are some exceptions, but for the most part, you get back the same data type that you started out with. If you ever find yourself not knowing what you're working with, this is just generally helpful, right? You can always call type on any Python object to see what it is. So if you ever find yourself saying, I don't know if I got back an array or a Pandas series, you can always just check the type this way. Okay. Now you can think of series in several different ways. So one is, I've already kind of mentioned, you can think of it as a generalization of the NumPy array. So it's internally storing this array, but it gives you some extra tools for accessing and manipulating that data. So for example, above we're letting the index assume its default values. So when you create a new series and pass some values in, it's going to assume that the index you want is just sort of 0, 1, 2, 3, et cetera. But unlike in NumPy, you can actually label those values explicitly. So you can say here, I want to pass in the values A, B, C, D. And that's your index now. The number of values here has to match, right? So that's very important. And you can verify that if you try to do something like this, it will complain because it's got 4 values, but you're only labeling 3. So that's a very common error when you're passing indexes in programmatically. You'll very often find you did something wrong and then things are not aligning. Pandas errors are not, I mean, this is relatively good, but Pandas errors can be a little difficult to make sense of sometimes, because Pandas internally is really a very complex piece of software. So as with many things, I recommend Googling, just copy and paste that error. At least when you're starting out, that's, I think, probably the easiest way to figure out where you're going wrong. In any case, in this case, we're initializing a series, we're passing the same values, but we're explicitly assigning these index values. And so now, this is the index, right? So now if we try to access B, we should get that same value, where before we had a 1, we now have a B. Any guess as to what will happen if I try to do this? Well, let's try and see. Still works, right? So the way you can think of this is that by default, if you ask for a particular key in that index, Pandas will first check to see in that series if that key exists explicitly in the index. And if it doesn't, then it'll fall back on assuming that you want the position. This can actually be a little dangerous, and I'll show you why. Suppose I had done something like this. Okay? So now I have an index, and you can pass integers as the index. So now my first row has the index, or my first value has the index 3. And so now you're in this very interesting situation where it's ambiguous, because now if I do this, right, what do you expect to get? Well, if you know how Pandas is operating internally, then the answer is, what's the answer? 0.25, right? Let's verify that's true. But, right, there is some ambiguity if you're not familiar with the rules here, because you might think, well, if you pass an integer, you should get back, that should be the integer index, right? So that should be the 4th value. So one thing to do in general, it's good to avoid, it's not a hard and fast rule, but I recommend avoiding making your index integers in general. Right? Use strings, use something more complex than that. This is arguably a bit pathological. And there's actually another way to get around this, which we'll talk about with indexing. You can actually avoid this kind of ambiguity using different approaches to indexing values, which I'll show you soon. Question? I thought, no? Oh, sorry. Yeah.
What happens if you do A colon or B colon D?
Okay. Okay, we can do that now, it's fine. Yeah, so this, I mentioned that I learned a couple things myself, actually, when I was reading through this. So if you had asked me like an hour ago, would this work, I would have said no, but, oops, sorry, D. But as it turns out, it does work. So you can actually slice using string values if the index is strings. But of course, you would have to know, right, that like D is like, you'd have to basically be saying internally, like, I want all the values up to D. So this would only make sense if there was some structure to your index to begin with. But you can do that, which is kind of interesting. And I wouldn't have expected it, to be frank. Other questions? Yeah.
So if you slice with the numbered index, then the index is also out of order. Then we run into the same problem. Is that correct?
Yeah, it will preserve the order. So if you were to, yeah, so like, you mean like if we had, let's try this again. Like this. And so you're,
just in the previous example where you just let it index automatically and then slice the like last 2.
oh, so you're saying like if I do something like C to D? It'll preserve the order generally. So does that?
But that's inclusive. So if you do 1 through 3, that same.
Oh, interesting. I didn't notice that. Ah, that's interesting. Okay, that's interesting behavior. I don't know what there's probably some reason for that, but there's probably a really long GitHub issue, right, where like there's like, actually this is true of Pandas like to a ridiculous degree. There's like these long threads of people, and it's good. People really kind of spend a lot of time thinking about this, but if you really want to know, I bet you can find like the detailed thought process behind why it works this way. I don't know off the top of my head. It's interesting. For the most part, I will say actually Pandas is very consistent. That's one of the things that differentiates it from, I think it's more internally consistent than R, where you can actually end up with some fairly odd situations because you don't have ways of preventing certain ambiguities, and I'll show you some of those in a bit if we have time. Okay. This is kind of neat, or you can use non-contiguous or non-sequential indices. So you could basically say, for example, you can actually pass, I think this is true. Oops. Right. Oh, whoops. sorry, we're now working in, let's, yeah. Right, so you can ask for multiple values. They don't have to be in order. You will get them back in the order you request them. So if you ask for B before A, you're going to get back a series of B before A. This can be quite helpful because if you have, you have a list of indexes and you want them in that same order, you know you're guaranteed to get in that order. You're not going to get them back in the order they appear in the initial series. Okay, so you can think of this as sort of a glorified array, but you could also alternatively think of it as a kind of dictionary as well. And so you can see this if you look at one of the ways you can initialize a series, which is from a dictionary. So hopefully you're familiar with dictionaries in Python by now. So here we're creating a pure Python dictionary. Right, so this is not a NumPy object or a Pandas object, it's just a pure dictionary. And if you wanted to pull out the value at this particular key, Florida, you can do so like this. So you can create a dictionary like this and pass it into a series, and that is just fine. That will construct for you a nice series as well. Now, I will make a note of that here that dictionaries technically don't have order. Right? So you're not guaranteed that the series will respect the order in the dictionary because dictionaries don't really have an order. As of Python 3, there is actually, all dictionaries are ordered dictionaries, so it might look like you have order, but don't assume that. Like, you should not assume that if you feed in a dictionary to this series constructor here, that just because you type this thing first, it's going to be first in the list. That's not a safe assumption. If you really need that order, then pass it like this. So pass the values explicitly and the index, and then you're guaranteed that it will always be in the order you want. And so just like with a native Python dictionary, you can now refer to a particular value by just passing in its key. And this actually addresses this is your question from earlier, right? You could have just said, like, give me all the values starting at California and going through Illinois. Yeah?
If you're using a new version of Python, dictionaries are.
Yes. Yeah, as of Python, I think 3 or maybe 3.3, all dictionaries are ordered dicts. But the only reason I say you shouldn't assume that is because you could be writing stuff that should run on 2. And in general, it's probably not. In most languages, dictionaries are not ordered by default. And so it's just not a good idea to assume that just because you're passing in an ordered dictionary, it will respect that. I'm actually not even sure that it will respect that even in Python 3.6 always. So, but that could be tested. Okay.
Are the states the index?
Yes. Yeah. Yes. In this case, the stakes are. And if you kind of want to verify that, you can always just ask for the index, right? So you can say, and the same thing for values. So you always have the option of finding out, like, what are the values that are stored, and what is the index. And don't think of these, even though when I print it like this, it looks like this is a table with 2 columns, right? But it's not. It's just the way it's represented. But actually, the index is a different kind of thing. It maps 1-to-1 onto the values, but they're represented separately in memory. They're not, well, this is probably not a good way to put it, but they're not, the index is not actually just another column, although it can be turned into one if you really want. Okay. There are several ways to construct series. You've already seen a couple. So the most common thing is this, which you saw above. You just pass in the data you want, typically a list or a NumPy array, one-dimensional array, and then optionally some index. So you can initialize a series from just a list of values. You also have this kind of neat trick. You can pass a single value. This is kind of similar to the way NumPy behaves. You can pass a single value, but pass multiple values for the index. And so implicitly what's going to happen here if you do this is Pandas is clever enough to say, oh, you're only giving me 1 value, but you have 3 indexes. You must want me to just repeat that value. Right? This is called broadcasting. You have to be a little careful with this. So I suspect, for example, that this should not work. Right? I'm actually curious if this works. It probably won't. No, OK. Well, just as an aside for those of you really familiar with NumPy, in NumPy, sometimes if you do this kind of thing, it will work because it'll realize that one is a multiple of the other, so it'll just like repeat one. But Pandas doesn't do that here. So this is a special case. It will only work if you just want to fill this series with the same value, but still have different indexes. I don't know that this is very common, but just to show you that you can do this. You already saw you can pass a dictionary. So here you're creating a series by passing in the keys and the values. Notice in this case, right, we've now the index is integers, the values are strings. So series can take on any type. They can be number, they can be floats, they can be integers, they can be strings. Although Pandas calls strings internally objects. If you ever want to know what the type of a series is, you can use this D-type thing. And in this case, if we do this, you'll see that it's actually represented as O, or object. But it really is a string for all intents and purposes. Well, it could be other kinds of objects too, in principle. Oh, interesting. There's another thing I didn't actually realize until right now. So this would be helpful if, for example, you have some variable you created somewhere else and you're feeding it into the series constructor, but you only want to keep some of those indexes and values, right? So you can pass in this thing, and you could have got this from anywhere. But as you're constructing this, you're basically saying, I don't want this whole thing. I actually only want to keep the values that have index 3 or 2. So you're essentially pulling out a subset of that while you're constructing this thing. Okay. All right, so that's just a very basic introduction to the series. Now we'll talk about data frame, which is really the two-dimensional version of a series. You can think of a series as one column, and if you were to take series and start stacking them next to each other, then you end up with a data frame. So you can really just think of this as like a two-dimensional generalization of what you've already seen. So here you have a dictionary, and we're creating a series. Right? You've already seen this. But now let's say we want to create a data. We have this other population. Let me just make sure that I initialize it the way it's initialized here. So we created this population series, which has states as keys and population as values. And then here we're creating an area series. So we're now creating a dictionary of the size of the states. So we have these two series. If you want to verify that, right, you can always just print both of those things. And so it's not printing it very nicely, it's just concatenating the two. But you can see that here's your area series and here's your population series. And let's say we want to combine these. I mean, these have the same key, so it's very sensible to represent the states as rows and both the population and the area values as columns of some bigger table. And a simple way to do that is just to pass in a dictionary of these two series now, right? So now we're creating a data frame by calling data frame from within the Pandas module. And we're passing in this dictionary. And the dictionary now has, as the keys, the names of the columns. So series does not, I mean, by default, the series does not have a name, right? So if you look at this thing here, there's no name information anywhere there. Like nothing tells you that this is called population. It's just a series, although you could set one if you wanted explicitly. So now we're in the process of passing in these values. We're going to say that we want this column to be named population, and we're giving it the value, the series that we created, and then we're passing in the area series and calling it area. And so when we look at what that prints out, here now we have a data frame.
So is a data frame a dictionary?
You could think of it that way. I mean, the nice thing about Pandas is in the sense that it gives you, so you can think of it as just like you can think of both of these things as both arrays or dictionaries in the sense that you can index into both of them by position or via keys, right? So I can't tell you off the top of my head how it's represented internally. Well, I guess it's the values are represented as a NumPy array. I'm not sure how the details of how the index is represented. And just like with series, you have an index, and the index here looks very familiar. And so this is actually a feature of the Jupyter Notebook, I believe, is it has sort of built-in representation of Pandas data frames. It doesn't show you this nice display for series for some reason. But this still is the index, and now you have your two columns here. Yeah?
Do the series need to be of the same size?
Well, hold that thought. We'll get to it in a second. The answer is that if you're constructing it this way, I believe they do, but there are other ways to handle that problem where they're not actually of the same length, but they have common keys. So we'll share that in a second. So the index you can get out, and of course you can do the same thing for the values, right? So if you do this, you're going to get now a two-dimensional NumPy array. If you're familiar with NumPy, you'll know that it has a shape. Every array has a shape attribute, so this is a 5x2 NumPy array. For what it's worth, data frames and series also implement the shape property, so you could always just ask what is the shape of the data frame, and it's also 5x2, not surprisingly. So you can always figure out the dimensionality of a series or a data frame.
If you had given it, the population and area had not had the states in the same order, would this have worked?
Yes. Yeah. So I'm fairly certain that's true. So yeah, it aligns them internally, right? So they're both series, and so it will know that you're basically always going to align these things so that, like, if you have the California key in both, then they're both going to be put on the same row. This can actually, there are some odd things can happen. I think we might get to them, but there are some weird behaviors in indexing. I would, in general, suggest that if you think you might run into those kind of situations, do as much of the validation outside of the constructor. Most of the time, it will do what you expect it to, but it's always good to, like, verify that, before you get to this point, it's good to verify that, if you're expecting them all to align properly. I wouldn't worry about necessarily putting them in the same order, but definitely make sure that you have sort of the same keys, et cetera. If you don't, most of the time it'll do the right thing, and I think you'll see an example of that in just a moment. Now, you've seen how to pull out the index, you can pull out values. You can do both of those things for series. However, data frames, because they have this extra dimension, right? They have multiple columns, also store an index along the column axis, and this can be a little confusing, right? Because you have an index is basically it's kind of what it sounds like. It's an object that represents sort of information about what either the columns or rows are representing. It's just unfortunate that it's called index along the row axis and columns along the column axis. But be aware that most of these things technically are considered index objects, as you can see here, right? So if you ask for the index, that's an index. But this thing is also an index. It's just that it's an index along the column axis. It's actually very sensible from, like, the standpoint of the internal representation, because they're doing the same things. And in fact, you can easily transpose the data frame just by doing this. Boom, and you've transposed things. So it makes perfect sense that the index is the same thing whether it's the columns or rows, but just to be aware that the naming is a little confusing. And so this just gives you back the information, just like the row index, about what is in those columns. So we know that this one is population, the first one is population, the second one is area. Okay, let me skip over this. It's essentially the same as we talked about series. Just as with the series, you can construct data frames. Actually, you can build data frames in many different ways. So you can take a single series and turn it into a data frame. So if I pass in this population, remember population is just a single series, and just remind you. So here's population, that's a series. But I can create a data frame from that series by passing in that single series and just stipulating that this series has the column name population. Now, why would you do this? There are actually several good reasons. The only point I'll make is that just because it looks like they contain the same information does not mean that that they're actually the same object. And one way to get a quick sense of that is that a data frame is always two-dimensional. So if I assign this to states and I ask for its shape, notice it has two dimensions. The second dimension only has one element, so it's 5 by 1. But if I were to look at the population, that series, that's one dimensional. It only has a length, right? And what the implication of that is that once you have a data frame, all the stuff that applies to data frames comes into play, and there are lots of functions you can call on data frames that you can't call on series, or vice versa. So you can actually you sort of treat a series as a data frame, and there are situations in which that's kind of helpful. But here that is to show you that you can initialize from various kinds of data. You can pass a list of dictionaries. This is really quite nice, and now we're going to kind of get to your question from earlier, right? So here, in this example, let me just kind of show you what the data looks like. So this is just pure Python. We have a list of dictionaries. All of them have the keys A and B. So if you just hand this to Pandas and pass it into the data frame initializer, it'll turn that into data frame. And it'll find all the keys and treat them as the columns, and it'll just sequentially take each element in that list. And here we have, again, just to show you, right? So we have these three lists. So this becomes row 1. This becomes row 2. This becomes row 3. Now, you might say, and some of you already asked, in a slightly different context, what happens if these aren't aligned? What happens if you have non-shared keys? So this first dictionary in the list has keys A and B, but the second one has B and C. And by default, Pandas is smart enough to assign missing values. So it'll just say, well, we're just going to note that we didn't have a value. And so it uses NumPy's nan, in this case, to tell you that there's no value, but it doesn't lose any information. You're still getting all of that information. It's just going to create, it's the union of all possible keys, basically. So you'll have as many columns as you have unique keys across all of the elements you feed in. We've already seen this. You can construct a data frame from a dictionary of series objects. You can also feed in, this I would say is probably actually the most common approach you'll see. You can also feed in a NumPy array. So let's say you've been working with a NumPy array, but now you actually want to label the axes so you can do Pandas stuff. So you can just pass in, let me just make it a little more explicit here. So we can say, we can create a new NumPy array. So, right, so you've probably seen this kind of thing before. We have just a NumPy array 3x2. And if we just hand that to Pandas, it will now wrap that in a nice data frame. If we didn't pass any other arguments, it would just label both axes automatically, starting 0 and numbering them. But we can explicitly pass both the columns and the index. So here we're saying we want the columns to be named foo and then bar, and the index to be named, the first row is named A, the second row is named B, and so on. And again, these must match. So the number of columns you pass has to match the number of columns in the matrix. Number of values in the index has to match the number of rows in the matrix. And it will complain if you don't do that, as you've already seen, right? Okay, I'll skip over structured arrays. Now that we have pandas, I don't think there's actually much reason to talk about structured arrays in NumPy. And actually, just in the interest of time, I'm also going to skip over the index object, except this is kind of neat. So when you pull out indexes, you can actually do set operations on them. So let's say that you have two data frames and you want to know, so here we're just constructing indexes from scratch, but you could have pulled these out of data frames. You could have asked for the index in data frame A and data frame B. And very often you want to do things like, what are all the common keys across these two data frames? Like, what are the observations that occur in both A and B? And you can actually do set operations on them. So in this case, if you have these two indexes in A and in B, and you'll notice they share some values, but not all, you can take the intersection with the AND operator. You could do the union. And you could ask for what's in one but not the other, right? So this is kind of cool. It makes it very easy to do set operations on index objects. It does not work for regular columns, but you can always turn a regular column into an index just by passing it to PD index, right? So you could pass population, and of course now this intersection is empty because the values for population are very large and none of them overlap with this. Okay, so that's sort of very basic introduction to Pandas objects, and we've already taken up about 60% of our time. But this stuff is really important, right, because it sets the background for everything else. Any questions before we talk about what you can do with these objects? Okay. All right, so let's talk about indexing, which is super important and is in some ways kind of counterintuitive. So the idea is obviously to pull out select chunks of information from our series and data frames. And you've already seen that we can call, here, let me clear these outputs. So we can index into a particular series just by asking for the key. You've seen that. You can use, let me skip over this because if you've seen this in Python before, the only point I'll make is that if you have a lot of the idioms you have in base Python as well, so you can treat series pretty much like lists in Python. But since some of you probably haven't seen this kind of thing, I won't spend any time on it. We've already talked about slicing, so I'll just skip ahead here. This is where it gets interesting, and this is important, but it's also can be kind of counterintuitive. So you've already seen that you can just call directly in some sense into a list, right? So you could just say, give me the value at index 2 in a series. But Pandas also gives you a bunch of what are called indexers, and they change the behavior of that index you're asking. So here's asking for the element stored at position, stored at index 1, and it's A, right? And when you're slicing here, you get, as we saw already, an implicit index. So you can actually say start at 1 and give me everything up to 3. But as I already mentioned, this causes confusion, right? There can be cases where if the index names are, if the indexes are integers, you can have this ambiguity where, like, if I say I want the value at 2, you don't know if 2 is like the third row, right, the 2th row, or if it's actually the value assigned to the index, which could be anywhere. It could be in the first row, the last row, etc. And the way that you resolve that ambiguity in Pandas is by having indexers that tell Pandas exactly what kind of what you're trying to access. Are you trying to access the value through the name of that row in the index, or by position? So the LOC, or loc for location indexer, basically stipulates that you are trying to get the row that has this particular index value, right? So this is unambiguous. This says, give me the value stored in the row with index 1. And if there's nothing there, it'll crash. It's not going to try to find this. It's not going to give you the second value, right? So this works fine. But let's say I do something like this. 2. Okay, 2 will work. Notice that we indexed here, right? Our indexes are 1, 3, and 5. There's no 2, even though 2 would be the third value, right? So if I do this, that fails. If I didn't have this loc thing, that shouldn't fail. Oh, I'm sorry. Interesting. Oops. All right, I'll look into that later. Okay, just for now, let's just say that what this ensures is that you never actually try to access the index by anything other than the value that's stored. Yeah, I think this will actually, okay, well, I'll try to come back to this when we talk about data frames. Now, if you want the position, right, so you might say, well, I actually don't want to access the row stored at index with value 2. I want the actual third row numerically. You have this iloc indexer, and that is always going to refer to the position within that list, within that series. And so if I do this, I'm getting a different value now. Okay, notice loc gives you A, iloc of 1 gives you B. Why? Just to make it very clear, let's display our series again. Here's our data, right? So the value stored at index 1 is A. But because we're indexing from 0, if you ask for the 1th value, right, so this would be 0, this would be 1, you're going to get B. And this may seem like a fairly pedantic distinction, but when you're writing code, it's super important to know whether you're referring to the location or the integer location or the index location by name. And so it's generally good advice. I mean, you do certainly fall into the habit of like writing something like this, but it's good if you don't mind the extra characters to get in the habit of always using these indexers explicitly. So because it removes any ambiguity, right? Someone reading this will always know, okay, you're trying to access values based on the index or based on the position in that series. Questions? So more characters, but this is sort of the Python philosophy. Despite being a very high-level language, in some ways is kind of paradoxical, right? The idea is, is that you want explicit is better than implicit. You want to make it clear what you're doing. Sorry, hopefully this comes back up. Okay. All right. Dictionaries follow kind of the same logic. So this is just repeating what you saw. We're constructing a data frame that looks like this. And now we can index, and this is also going to be a little counterintuitive. If you pass a single value, if you just try to pass, you have this data frame. Remember, this has, we know because we're looking at it, right? It's two-dimensional. It has multiple rows, multiple columns. If you just pass it a single value to index, like area, by default that's treated as the column name. So this is actually saying, give me the name, give me the entire column area, which I believe is how R behaves. It's how other things behave. So that might not seem super unintuitive. Notice that you don't have to explicitly pass both axes, right? So you might have thought that, if I wanted, so for example, in NumPy, right? Oops, what did I just do? In NumPy, if you want to say that you want the entire column, you'd have to do something like this. So it's actually the opposite of the behavior. In fact, I'll show you that, like, if these are the values in NumPy, oops, and I were to do this, does anyone know what I'd get? It'll work, but it'll give me the first row, okay? And if I wanted the first column, I would have to actually explicitly say, take all the values in the row axis and give me the first column. Pandas, curiously, does the opposite, right? If you only pass a single value, it assumes you're talking about columns. And I think this is probably out of respect for other kind of environments that do this, where usually columns are the thing you're referring to first. But it can be a little tricky. Let me skip this stuff. The solution to this is the same kind of idea, right? So you have, to avoid ambiguity, it's a generally good idea to get into the habit of always passing in these iloc or loc indexers. Again, it's annoying, but it's just 3 extra characters, 4 extra characters, and it makes it so that you can always refer unambiguously. Or, alternatively, you can always get in the habit of adding in that extra axis. If you do this, oh, right, that doesn't work. It would have to be, yeah. Right, sorry. So yeah, you can't actually even do what you would in Python, which is like, say, this you might interpret as like, give me all of the values in the row that corresponds to the area column, but it does not work. So there used to be, there still is technically, an IX indexer that allows you to do both of these things. So it allows you to, it's sort of roughly what R does, right? So it's clever in the sense that if you do something like this, notice it says it's deprecated, so you shouldn't do this anymore. I'll tell you why right now. So if you do this, Pandas is smart enough to figure out, oh, what you're probably saying is you want the first 3 rows for the column pop, or for all columns up to pop. It's easier to interpret if you just do this, right? So you might say, what's wrong with that? Well, for reasons I've already shown you, it can be ambiguous. Often you end up in a situation where it's not clear whether you're referring to integer values or to the names of actual, to values in the index. And so you can completely avoid that kind of ambiguity by doing this. If you use iloc, you're saying, so what this means is give me all the rows up to the 3rd row and all the columns up to the 2nd row, up to the 2nd column, right? So that's how you're applying the subset. And if you do this, you'd be saying, give me all the named rows up to Illinois and all the named columns up to pop. And that's unambiguous. Again, I know it seems annoying. It is a good habit to get into because you will avoid pain down the road. Any questions about this? This is, I think, one of the most kind of difficult things to learn. It's just because you're learning, it's just the way it is, and you have to learn it. But it does actually make sense if you think about the underlying logic. But if you have any questions at all about this, now is a good time to ask about indexing, like how you pull out subsets of values from data frames. Okay, there's no way that everyone in this room is totally on board with all of that, so. Okay, well, feel free to find me later if you have questions.
Actually, can you touch real quick on what colon Illinois, that syntax is? I figured it out like 2 seconds ago, but I was.
So it's everything up to the actual value Illinois. I generally don't like this personally. I think it's, this it's a little confusing, right? It's not, I wouldn't actually, oh, sorry, you mean this here?
No, I mean,
oh, you mean like
I get it with the, like I got it when they were both there, and it's just colon Illinois. I was like, what?
Yeah, so this will give you all the columns up to, wait.
You're in the quotes.
I'm what?
You're in the quotes.
Oh, sorry, thanks. Yeah, so again, because by default, if you only pass a single value, it's interpreted as the column axis, right? And that's where it gets counterintuitive. This is why, again, I would suggest staying away from this. It's very natural to pick out only a column. I do this myself, but I would still say, like, do as I say, not as I do, right? Like, if you want to pull out the column Illinois out of this data frame, let me remind you what the data frame looks like. Or sorry, oh, actually, that's even weirder. Okay. That's interesting. Okay, so this is even more counterintuitive, right? So I'm glad you said it because this is another reason why you probably you want to always pass both axes. So just to make it clear what's going on here, I avoid the syntax for rows, which is why I didn't actually know this even happened. So here's our data. This is our data frame. If you say this, that's not going to work. because if you pass a single value here, it's expecting a column. So if I had said instead area, no problem. It's looking for the column. So it's a little weird, right, that this should work. So if you do this, now somehow magically it thinks, oh, that applies to the rows. Again, you avoid this if you are always explicit that like if you want the rows, then just say, first of all, use the location indexer. And secondly, it's good practice to always, we know that there are two axes. This is always the rows, this is always the columns, right? So just be explicit, and then there's no ambiguity. Like you always know that you must want all the columns because there's that colon, and you must want all the rows up to Illinois. And also this prevents errors because if I had done something like this, it wouldn't work because there is no column Illinois. Okay, so the moral of the story is be explicit. It's very easy to fall into the trap of like picking out a column by doing this. I just want the area column, I'm just going to really quickly retrieve it. It will work, but it's probably better if you get into the habit of doing this, even though it's a little bit of a pain. Your code will thank you later when you're debugging and you realize that it's not clear whether this is a row or a column. And this is not hypothetical. Like I've run into this many times, and increasingly I've just forced myself now to do this. And if you come from R, right, like R doesn't really think about many of these issues, and you will run into the same problems, but you won't know it, and then it forces you to do everything explicitly yourself. And here you have conventions for just making sure that the code stipulates exactly what kind of information you're trying to access. Other questions? I'm happy to spend more time on this because I think it is actually quite important. Even if you can get away in many applications by doing just this, it's good to kind of understand a little bit how the indexing is working. Okay. All right. So I'll probably spend the remaining of the time on, let's actually skip this. Let's skip the next few sections and talk about concatenation and appending data. And I'm just going to focus on like some of the most common applications. You have multiple chunks of data, you want to combine them in some way, you want to aggregate. So what you're seeing here, I'm not going to go through, it's just a little helper function Jake wrote that displays data frames nicely. So you can ignore this, you can certainly work through it later and figure out what it's doing. But the idea is just it's a nice way to generate data frames with a certain structure, just a little helper function. And the same thing here, this is just a nice little utility that you'll see in a moment that just displays multiple data frames alongside each other so it's easier to see what we're doing. Now, if you're familiar with NumPy, and some of you have just been introduced to NumPy, you probably haven't talked about concatenation of NumPy arrays. But just to show you, right, that if you in NumPy concatenate, so you define these three lists here, and then you can pass NumPy's concatenate function a list of these lists, and what it will do is it'll just append them one to the other, right? It'll just tack on in the order you pass them. So the result of this is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this hopefully is pretty intuitive. And this works because each of these arrays has one dimension. So there's no ambiguity about like, well, do you want me to stack these below each other? You know, there's only one dimension, and so you just kind of are adding to the end of the previous array. But if you were to pass in explicitly a two-dimensional array, so here we're creating X, and X is a 2D array, we can ask, or I should say a 2D list. Let's, just to be explicit, let's say we initialize this as an array, and we ask for its shape. It's 2 by 2, and you can see the structure there, right? It's a list of lists. Here's the first row, here's the second row. What happens if we try to concatenate X with itself? And there's our answer, right? So this right here is one copy. This is what X looked like, and just by default, NumPy will stack the next version right below it. Why is it doing that? Why doesn't it go along the other axis? And the answer is because by default, it stacks along the 0th axis, which is the row. So this is equivalent to doing this. So you have this 2 by 2 thing, right? And by default, if you ask to concatenate with another 2 by 2 array, let's say, really anything with 2 columns, it'll just add it below, and so on. But you could say, well, I want it to actually stack along the column axis, and that would be saying X equals 1. And so now it's going to have that X, and then it'll put a copy of itself right next to it over here. Right? And the reason I'm showing this is because Pandas operates in a very similar way. And in general, the logic that you find in NumPy tends to transfer pretty consistently to Pandas. There are some exceptions, but by and large, if you know how something behaves in NumPy, it will probably behave the same way in Pandas. It doesn't have the same name. In Pandas, it's called concat, is the concatenation method. But the idea is roughly the same. So here, if we create 2 series instead of 2 NumPy arrays, so just to kind of remind you, right, here's the first series and the second one is DEF, and we concatenate these 2, same kind of behavior. It just depends the second one to the first, A, B, C, D, E, F. So you can pass in a list of as many series as you want, you'll just get one that concatenates all of them. You can do the same with data frames, but data frames, remember, have 2 dimensions. So now it's the same principle. Now you have to actually, you don't have to be explicit, but you have 2 options. You could stack those data frames along the row axis, or you could put them next to each other in columns. This display utility that Jake makes is just a kind of a nice way of, we can pass in a bunch of arguments, and so this is really saying evaluate each of these as if they were Python commands, right? So it's just like, what's going to happen is that it's going to show, it's going to like print the result for df1, and then it'll do the same for df2, and then it'll do the same thing for this PD concat. So just imagine this was Python code instead of a string. And it's just mapping like this Python code produces this Python code produces this Python code produces this. And what you can see is that by default it does the same as NumPy. It stacks them one after the other. Again, explicitly if you want, you can actually say, I want to stack these things along the column axis. This does not work because of a change to Pandas. So this was written, actually, Pandas changes pretty quickly. This was written like last year, and this apparently doesn't work. The reason is because I think you can no longer pass axis equals col. So you have to do the way you do in Pandas, which is specify the order of that axis. So axis equals 1, which refers to col, still works. So that's just, it's not a bug, it's just the notebook is a little bit out of date. But same principle, right? Here we're saying, in this PD concat, we're saying, and just to kind of make it very clear that this is just like a little helper utility, we could have just done this and it will give you just that result, right? So we're saying take a list containing data frame 3 and data frame 4 and concatenate them along the column axis. Questions? Okay, concatenate is super helpful. Now, what happens if you have duplicate indices? And so notice in this case, when we create these data frames with this make df thing, so if we run this, if you just look over here and then here, right? So this data, both of these data frames that we're trying to concatenate have the same indexes, 0 and 1. And so you might say, what's going to happen when you try to concatenate those? Is it going to say, well, you can't do that because you have data frames with the same indices? And the answer is no. It doesn't really care about that. It'll just concatenate them, right? And it's probably the behavior you want. It's not really relevant that they have the same index. You probably know what you're doing by concatenating them. As just a little tip, you can always reset the index. So if you do this, so if you know that some of these things are going to have the same index, but you later are going to want to pull rows out of this without ambiguity, notice if I say x, y equals, right? And now if I say, okay, it's going to give you 2 back. It's going to give you both of those things, which might not be the behavior you want. You can always reset the index by calling reset index explicitly, and that will just go sequentially and number them like 0 through however many rows you have. So this is very common after you do these kind of operations to just reset the index just so that you don't have any ambiguity. Alternatively, of course, you might want to retain the same index so you can pull out multiple rows, and that's fine, but you have the option.
The old index too?
Sorry?
Does it keep the old index as well?
No. So what you can do, well, actually, I take that back. So if you have, so here. So in this case, so it will by default, right? So when you call reset index, it takes whatever was here, and you can see it makes a column. If you don't want that, which you often don't, then you can pass the argument drop equals true, and then it won't include it. And reset index, like most things in Pandas, have all kinds of different options. So you can control the behavior of that reset call. It can sometimes actually be very helpful to have, like you want to treat the index like it was just another column, and so you actually call reset index that way. Okay, let me skip over this. Definitely not going to talk about multi-indexes right now. Okay, append is worth mentioning. Append is just a really quicker way of calling concat. So if you just have like one data frame and you want to tack on another one to the end of it without any sort of fancy behavior, then you can just say data frame 1 dot append data frame 2, right? You're saying, like, you're basically calling it on this one data frame. You're saying, hey, buddy, append this other thing I'm giving you, and it will just tack it onto the end. It's more limited. Any question about concatenation? Okay. All right. Let's talk briefly about merge. I'll just pick out one or two things, and then the thing I really kind of want to spend just a few minutes on is aggregation and grouping. We don't want to talk about that. We don't want to talk about that. Okay. I mean, I definitely recommend if you think you're going to spend time in Pandas, I recommend working through all of these sections and actually running the code and playing with it. It'll give you a much better sense of what's going on. But just to kind of give you a flavor of some of the most important things, I'm going to talk a little bit about merging here. So you've already seen this utility, just shows you data frames. There are lots of ways you can merge data frames in Pandas. It has really pretty sophisticated tools for merging multiple data frames. So let's work with these two data frames here. So notice that we have, so what we have here, we have it's essentially a directory of employees, right? So we have the employee name and then the group they're assigned to in one data frame. In the other data frame, we have also employee name, but now we have the hire date. And this is very common, like some of you probably used to working with databases, right? We have multiple databases or multiple files, they have information, you want to join that in some way. So just looking at it, we know that these rows correspond. Like we probably want to merge these into a data frame that has Lisa as a row value, and then the value engineering for group, and the value 2004 for hire date, right? So you want to align these nicely. And so I think this came up with a question earlier. We can just pass those directly to the merge function. We call pd.merge and just give those two data frames. And by default, what Pandas is going to do is it's going to actually look at the indexes. So it's assuming that when you're merging two things, there has to be something in common, right? You're trying to merge those on some common piece of information. And if you don't tell it anything else, then it's going to assume that you're trying to match on the indexes. And so in this case, it gets it right because these indexes all align perfectly. And there's our result. So we have Lisa, who is in engineering and was hired in 2004. Jake works in engineering also and was hired in 2012. Very simple. This is the best case scenario. We have all the same keys, and you're just doing a simple thing. Okay. Now, often you're not in this kind of situation. We have one-to-one maps. You often have like multiple values, multiple potential values in one data frame and like one target in another. So in this case, we have over here, notice that we have now the common key is actually going to be group, right? So now we're going to try to join, the sensible way to join these two tables is by looking at the common thing, which is group. But notice that there's one row for engineering, because this is telling us who the supervisor is for each group. But there's two employees in engineering, Jake and Lisa. And so now we're going to want to join or merge these in a way that respects the fact that we probably want to keep both of the employees and just duplicate the information at the group level. And if you just call merge without any arguments here, you get this thing. And that's exactly what we want in this case. And so what's happening here is that Pandas is smart enough to figure out that like the common column here is group. And by default, it's doing the outer join. So it's going to basically duplicate these rows as many times as it needs to make sure that there's a value for every employee. Actually, take that back. It's probably doing a left join by default, I think, because the idea is it's giving you as many rows as there are in the left data set, and it'll fill it with values in the right one. Now, the nastiest case, but unfortunately probably the most common case, is when you have many-to-many joins. So here you have a situation where you have multiple values for, so you have basically for every, let's see, yeah, so you can see that in this case, for every group you have actually multiple, for every employee you have actually multiple skills, right? And so, and for every group you have multiple employees. So if we merge this by default, then it does does it do the right thing here? Employee Bob. Yeah, I think that's right. So yeah, so in this case, it'll basically just it'll just duplicate these rows as many times as it needs to in order to end up with a full mapping, right? So it doesn't, basically, it doesn't, you don't want to end up with like a dropped value. Now, that's all the defaults. In general, I don't recommend you pass things to merge without explicitly specifying the arguments. And yeah.
This is like a particular area where I worry about making errors. I don't know if it's actually the most common place to do that. Do you have any?
Yeah, so that's a perfect segue, right? So I would not start calling merge without like specifying exact, so same principle as I mentioned. Just like it's a pain in the ass to actually specify the indexes or what the indexers, but you do it because it minimizes the probability of error. This is exactly the reason why, even if you know Pandas well and you don't think you need to pass those arguments, it never hurts, other than typing a little bit more, to actually specify what the join column is. And so that's what you're about to see here. So merge takes a whole bunch of arguments, and it's clear if we just, right, so if we do this. So lots of parameters you can use to control the behavior of that merging function. And so here are our data frames, and right away you'll see that you have this on column. So what is on? On is basically shorthand for saying, if you know that both of these columns share, both these data frames share a column, which they do in this case, right? We know that in all of these examples, like in this case, group is common. And so you can say you want to join on group, and that is making it very explicit. Pandas doesn't have to guess. It doesn't have to try to figure out what is the column that maps, that makes sense of this whole thing. It knows that it's going to use that column you just specified, group, as the key that's joining these two things. So that's a simple example where if we say merge on employee, just so you can see what's going on here, right? So this is the same example you saw earlier, and it's going to produce exactly the same result. So you don't have, in this particular case, you don't have to pass the on argument, but it's a good idea too, because it does, because then if someone else is reading your code, it doesn't require them to know exactly how Pandas is behaving, right? And also you will make errors. Like you said, it's very easy to change something, change it slightly, and all of a sudden you don't want to index on that, merge on that same column. On is nice when you know that the same column exists in both data frames, but often it doesn't, right? Often they're called different things. So in this particular case, notice this data is not normalized properly, right? So often you're pulling data from one place and parted from another, and it's very common that like in one file you have the group information and the column is called employee, but in the other file, which has the salary information, it's name. But you know that these two things are the same, so you want to join them, and the way you do that is by explicitly saying for the left data frame, which is the first one I'm passing in here, df1, right? Use the column employee. So left on means for the left data frame, the first data frame, so sorry, this is like, it should be like this, right? So the left one is the first one, right? So use the column employee for the left data frame, use the, for right on, take name, and merge them on that. So now what's going to happen is that Pandas is going to take every value it finds here for employee and try to match it with the equal value in the name column. And so that succeeds just fine in this case. Let me ignore drop here. You can also do left index and right index. So sometimes, remember, indexes are not normal columns. So you can't say, like, you wouldn't be able to say on index. Why not? Because there isn't any column named index. I mean, you know this is the index, but that's not a named column. So you can't do that. But if you want to merge on the index, then you can say left index equals true, which will say, hey, for the left data frame, I want to use the index column, or the index, not a particular column, and the same thing for the right. So this is very flexible because you can do things like, well, I want to merge, I want to use the index of the left data frame and a column named employee for the right, right? And you have that flexibility. All right, let me see if there's anything else. I'll skip this. Okay, last thing I'll talk about because I think it's kind of important. Although it will seem fairly unintuitive until some of the other, I think until you use some of the other stuff, but is aggregation and grouping. And grouping in particular, I think, is sort of a nice feature in Pandas. Not uniquely nice. I mean, you can do essentially the same thing in R and other languages. But I like the Pandas support as well. So again, we'll call this. And we're going to load a data frame from Seaborn. This is a planets data set. You can see it has the method of I think it's how I think that's really the measure of the planet's orbital period, mass, distance, year, etc. Over 1,000 rows. Extrasolar planets discovered up to 2014. I guess is the method that was used to discover the thing. Now, very often, when you have a bunch of data, you'll want to summarize it, right? So let's say you know that you have data like this, and you want to know, for example, well, I want to know the mean mass for all planets that were discovered using the radial velocity method or something. And so, oh, we haven't imported NumPy. And so the series implements a bunch of functions that you can call just in one series. And this is a very simple case because you only have like one row of numbers, right? So there's no ambiguity about what you're referring to. So if we have this series, which is just a set of random numbers, we can call sum on it, and it will give us the sum. We can call mean on it. As always, if you want to know what other things you can do with the series, you just have to look, and so you can probably infer that abs is absolute value, which it is. So this takes the whole series, and for every value, well, it doesn't matter here because they're all positive. But if we had negative values, it would turn the positive. I believe this should work. Standard deviation, and so on, right? So these are all sort of simple summary functions built into the series object. Now here we have a data frame, and the same principle. If you call just mean on a data frame, it'll assume you're operating on columns by default. So if I do df.mean, it's going to give me the average for A and the average for B. However, I could easily change that to operate on the rows by specifying the axis. So now I'm saying axis equals 1, which means take the mean along the column. And so now you have the mean for every row separately. And this kind of stuff makes it very easy to summarize data really quickly. And as you can see here. Let me skip describe for the moment. I want to get to group by. How many people have heard of the split, apply, combine strategy? Okay. Just a few of you. Okay, so this is an extremely popular strategy. I think it was introduced by Hadley Wickham, well, popularized, I should say, by Hadley Wickham, like so many other things in R. And the basic idea is that you very often have this pattern, right? We have a data set, and you want to split it into subsets. So maybe you have, I don't know, multiple observation for different subjects, and you want to take every subject, do something with their data, get a summary. Like you want to take every subject's reaction times, take an average, and then concatenate those together. So it's called split because you're splitting on some variable, you're applying some operation to that subset, and then you're combining the result back together. Extremely common, extremely powerful approach. If you master this, you will find yourself writing a hell of a lot fewer for loops, and you will probably have a lot fewer errors in your code, and your code will be just much, much shorter, as you'll see in a second. So here's sort of a schematic description, right? You start out with this input, and you kind of, let's say, are splitting it by the key, and you have now these three subsets. You apply the sum operation to each one, and then you bring them back together. Right? So here's our data frame, and the Pandas follows the strategy very cleanly. So if you take any data frame, you can call group by on it, and that's doing the split operation. Group by basically says take that data frame and split it on whatever value you pass it as you're telling it what column you want to use to split on. So in this case, if I say df group by key, I'm saying take this data frame and basically split it by the key. So you're going to put all the A's together, all the B's together, all the C's together, and that's it. We're not doing anything else. We haven't yet told it what to apply. It's just an object that sits there. It's called a group by object, and it's not doing anything. But internally, it's now represented as a sort of a series, or I should say a list of different subsets of that original data frame. And now what I can do is I can start calling aggregation functions on it. So for very simple built-in functions, I can actually just call them tack them onto the end of that. So df group by key, remember, is internally grouping by key. And if I just add sum to the end of that, it's going to apply the sum function to every group. Right? So in a very little code, no for loops or anything explicitly, we could take that potentially very large data frame and apply an operation to every group within that. Let me skip this. You can, if you want, explicitly iterate over groups. Iteration in Pandas structures generally is a little slow. I mean, it's not really slow. It's just not as fast as sort of built-in application operations. But you can, if you want. So let's say you take the planets data set we had, and you want a group by method. and you just want to yourself explicitly loop over those groups. So the iterator here, so you have planets and you're grouping by method, and then you're just saying for every group in that group thing you just created, do something. And you'll notice that you get back two variables for every group, and that's the value. So in this case, it's the method because we're grouping by method. But it's the value of, so and if we were working with our earlier example, it would be A if we were grouping on key, and then the group itself. And so you'll get hopefully a sense of this from the example. So actually, let me make this is a little confusing. Let me make this more explicit. Let's say, okay. So what's happening here is that we're printing that method, which is just the value of the group. So here's like the first group it detected in that when group method is astrometry. And all I'm doing here is I'm taking that entire group that we've just been handed, and I'm counting the number of observations in the method column. So sort of explicitly, I'm basically counting the number of rows within each group. This is actually identical. That's why I said, like, you probably don't want to, if you can help it, you don't want to do this, because I could have done this much more easily just by saying group by method count, right? Same thing. It does the same thing for every column, which is why you get the same exact information, because the count is always the same for every column. But it's the same thing, and this is going to be produced faster. But the idea is if you have something really complicated you're trying to do with each group, that's not built into Pandas. So you can set up this loop and then explicitly call do whatever you want with each group. Skip this. Okay. I think this might be where I'll stop. I'll just show you the aggregate, filter, transform, and apply methods. These are incredibly powerful. I would say that like maybe like half the benefit I get personally out of Pandas, and I work with Pandas a lot, is actually these things. So if you learn these well, you will be able to just dramatically shrink the amount of code you write. I mean, a lot of stuff ends up being done through these, again, split, apply, combine strategy with these particular tools. So here we have a data set, or data frame. And you've already seen how you can aggregate for built-in simple things like sum. And so if I just wanted to sum the value for this column for every key separately, then I could just do df group by key data 1 sum. Okay, and that just sums the number, sums the values for all the A's separately, all the B's, et cetera, for this column. But very often you have some arbitrary aggregation function. It's not available in Pandas out of the box. And so what you can do here is you can actually call aggregate, and aggregate then expects you to pass one or more functions. They could be anything. Any Python function that it can handle a data frame input, you can handle. And so what's happening internally is it's grouping by the key, it's splitting into subsets. Each of those subsets is being passed to whatever function you gave it. And you can actually give it multiple functions in this case. So what we're saying here is, hey, please take these grouped subsets of data and aggregate them, but aggregate them with each of the following functions. We want to get the min, which Pandas understands as the minimum. We want to take the median. Notice we're passing a NumPy function here. NumPy can handle this kind of data. And we also want the max, and that's coming from base Python. And it very nicely gives you, so this input that in one shot gives you back a data frame that has, for each of the columns in your data frame, for each group, the aggregated value for each of the functions you passed it. And you just have to make sure that each of these functions gives you back one value. Technically, it doesn't have to be one value, you just have to all return the same dimension. Very powerful, and I'm sure this is like, I remember being very confused by this kind of stuff when I saw it at first. If it's new, don't worry about it. I'm just trying to give you a sense of like what is possible once you actually learn this. It becomes or much easier to do a lot of fairly complex operations. Same thing with filtering. I won't get into details. The point is just that you can filter groups, so you can do the same thing, right? So for every subset of the data, pass some filtering function, it checks whether the entire group meets some condition, and it only keeps that group if it does. And so you can very quickly throw out data that you don't want that meets very complex conditions. And transformation is, in some sense, the most well, I shouldn't. I'll take that back. Aggregation obviously reduces the data, right? So aggregation takes like lots of data and it aggregates it and reduces some smaller representation of it. And transform is for cases where you're returning the same shape of data. So here's our data frame. And suppose what we want to do is we want to demean. So we want to take each of these columns and we want to return the value minus the mean within group, right? So remember, we're grouping separately for each key, and then we're taking each of these columns, and we're going to subtract the mean for every value. But the mean is computed on all of the rows in that group. And so just to show you that it works, what's happening is we're grouping, always this group by thing, right? And then we're transforming, and we're passing a lambda. If you haven't seen lambda expressions before, I don't know if this is helpful for those of you coming from JavaScript and many other languages. It's an anonymous function. It's a function you're defining in the moment. It will cease to exist once this code is executed. It is identical to doing right. So this is probably clearer. But it's the same thing. It's just a more compact way of writing that. So that transform function receives a function as its argument. And so every group is going to be handed to this function we just defined. So it gets the data for the first group, all the A's, and it subtracts the mean of the A's from every element, and it returns that in, right? So again, very powerful way to apply very arbitrarily complex functions to all the elements of every group. And last thing, and then I'll stop, I think I'm running over, is apply, which is just like a really quick, a simple way to apply a particular function to each group. And it can be completely arbitrary. So you can apply, in other words, there's no constraint on what's returned. The only constraint is that your function has to return the same shape for every group, right? But you can return anything you want when you call something and apply. So let me see. So here's our data frame, and what we're doing here is we're actually dividing the value in column 1 by the sum of the values in column 2. So we're actually using multiple chunks of information. We're using multiple columns, right? So in this case, for example, for the A's, we're going to take the value 0 and 3, and we're going to divide that by the mean of data 2 for those rows, which is 5 and 3, so 4. So basically, this value will be divided by 4 to give 0. This one will be divided by 4 to give 0.75, I believe. Okay, I probably got the numbers wrong, but hopefully you get the gist of it. And the point is that apply is completely generic. I mean, you can pass essentially any function you want, and it'll be handed each subset, and so you can do all kinds of stuff with them. Again, I mean, there's no expectation that if you're seeing Pandas for the first time, most of you haven't seen the split apply combine strategy. I don't want you to think that if you don't, this doesn't make perfect sense, that you're doing something wrong, right? That's not the expectation. Like, you shouldn't. I mean, you're a genius if you see this and it all just makes perfect sense and you can start writing code, right? The idea is, hopefully you can see the power of how you can sort of express very complicated data processing ideas in really small chunks of code once you master this strategy. And it's implemented in Pandas. Nothing compels you to use Python, and you can do the same kind of thing in R. MATLAB probably has an equivalent. The really important thing is the conceptual kind of idea of what you're doing here. You're grouping, you're applying something, you're bringing it back together. That is an enormously powerful strategy that you can use almost everywhere in data analysis, and certainly in imaging. So I'll stop there. Is there anything scheduled after this? Yeah, okay. What's that? Deep learning, okay. Is Ariel here? Okay.
Maybe they're waiting outside.
Well, I'm going to keep talking until someone comes and tells me to stop. Okay, any questions? Yeah.
So you could, like, sort by group, you could filter out a group, run some sort of transformation on the other group or groups, and then recombine. Right? So, like, one group might not have had the transformation applied and then recombine them?
Yeah, sure. Yeah, sure. So, yeah, absolutely. So, probably the way I would think of that is you could imagine. And there's many ways to do these things typically, but so like one, just what seems intuitive to me is you would separate the data set into the subsets that meet some conditions and that don't. Maybe you apply something to ones that don't, and then you concatenate them or something like that, right? So you can use that to like normalize the ones that have some value, change them somehow, and then bring them back together. Yeah, and that would probably be like 2 or 3 lines of code. Yeah, and yeah.
Can you go back to the for loop iterating over loops?
Yes, sure. Where was that? Hey, Mark. Where is that? Is it in this? Yeah. There we go. The group by object. Yeah, here.
Can you explain the syntax maybe for the loop, like where did method and group come from? Are those
Sure.
separated by?
Yes. So actually, one way to kind of see it is we could have instead of what I'm doing here is called parallel assignment. So it's probably easier if I don't do that here. So let's say I just assign this to object, right? So what I'm getting now. So for every group in that planet's data frame, I'm going to get back this object thing. Now let's see what's actually in this object thing. Well, let's print only the first one. So we'll only do the first one, just so that you get a sense of what's happening here. So it may not be completely obvious, but this is actually what's called a tuple, which you can think of as a list. It's actually just a list that you can't modify. It has 2 elements, notice. So here's the first value, and then the rest of this stuff is the second value. Okay, and all we were doing earlier is we were assigning these in the act of creating that for loop. We were doing it so we're basically saying, and again, this is sort of just a trick in Python, that you can actually assign these at the same time. So because we know that it has 2 values, we're in parallel assigning these 2 elements. I would have probably called one name and the other the group. And so now that astrometry is going to be assigned to the name, and in every group, the name of the group is going to get assigned to that name variable, and the group is going to be the actual data frame. Does that make sense? Okay. But if that doesn't make sense, this is like parallel assignment is a fairly unintuitive thing that you can do in Python, so don't worry about it. Okay, Ariel, just kick me off whenever I'm just answering questions, so like now good?
Yeah.
Okay, all right, I'll end it here. Feel free to find me afterwards. I'm happy to answer questions at any point during the next week and a half. Thanks.